नमस्कार बच्चों, मेरा नाम तन्या और हम लोग ग्रेड 11 केमिस्ट्री का 4th लेसन सीख रहे हैं जिसका नाम है केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर. Okay, in my previous video we learned about hybridization and how hybridization could guess the geometry of the molecule. Okay, so hybridization gives the geometry of the molecules, but it could not tell about the shape of the molecule. So that is why the VSEPR theory came into play. Okay, so with the help of VSEPR theory, which is nothing but valence shell electron pair repulsion theory, we can learn we can understand the shape of the molecule. Okay, so today we will be learning about the valence shell electron pair repulsion theory and how we can understand the shape of the molecule. We will also understand the difference between geometry and shape. Okay, now consider the three molecules. Suppose it is methane, we have ammonia, water. Consider the three molecules. Okay, so in the last video we learned about calculation of Z. Yes, if we calculate Z, we can understand the hybridization. Right, now Z is equal to, so I'll just write at the side the formula of Z. Last time in the last video I had given half of number of valence electron of the central atom, valence electron of the central atom, okay, plus the negative charge, we add the negative charge. If there is a positive charge present, we reduce it, we minus it, plus the number of monovalent atom, number of like hydrogen, fluorine, chlorine, etc. Monovalent atom, the number. Okay, this is how we calculate the value of Z. If we know the value of Z, we know the hybridization. So finding Z for the first one, methane. Okay, so Z is equal to half of number of valence electron of central atom. We talk about the central atom. Central atom means the atom that is less in number. Here it is carbon, so the configuration is, the atomic number is 6, so 2, 4. So we have 4 plus, there's no negative or positive charge, but there is monovalent atom, hydrogen. How many are there? 4. So we have half of 8, which is equal to 4. Okay, now for ammonia, second one, which is ammonia. Z equal to, nitrogen is a central atom, less in number. So 2, 5. So I have half of number of valence atom is electron is 5 plus, there's no positive or negative charge, but I have monovalent atom, which is hydrogen. How many number? 3. So I have half of 8, which is equal to 4. The third one, I have water. Okay. Now here, the central atom is oxygen, which is less in number. It is 2, 6. So 6 is the valence electron. So Z is equal to half of 6 plus, there is no positive or negative charge, but there's monovalent atom hydrogen, 2 in number. This is also equal to 4. So we got the Z value of the three molecules. Okay, all are same. And we know if Z value is 4, it is hybridization is sp3, right? It is sp3 hybridization for the geometry. I'm talking about the geometry is tetrahedral. Yes, and the hybridization is sp3. Okay, here the hybridization is sp3. Here also the hybridization is sp3. And if I talk about the geometry, it is tetrahedral, right? Geometry, not the shape. I'm talking about the geometry. For all of them is tetrahedral because Z equal to 4 and the hybridization is sp3. Okay, I hope till here it is clear. In the last video, we had done this. Now, the Z value is equal to the number of bond pair plus lone pair. Okay. Now, always remember Z value is equal to the number of bond pair. So it's the sum of Z value is the sum of bond pair plus lone pair. Okay, so this you must remember. Now, in the first one, methane. Okay, so this I'll write it at the side over here with another color ink. Z is equal to what? It's the sum of bond pair plus lone pair. Bond pair plus lone pair. Okay. Now, here, in the first case, methane, Z is equal to 4. It is sp3 hybridization. It is tetrahedral. Yes. Now here, each carbon atom is bonded to, the carbon atom is bonded to how many hydrogens? 4 hydrogens, right? So how many bond pairs are there? There are 4 bond pairs. That means how many carbon-hydrogen bonds are there? It is 4 of them, right? 4 carbon-hydrogen bonds are there, right? So 4 carbon-hydrogen bonds are there. So that means there are 4 bond pairs and how many lone pairs? 0 lone pair, right? So in the second one, ammonia. Z is equal to 4, yes. And nitrogen is bonded to how many hydrogens? 3 hydrogens, right? So that means how many nitrogen-hydrogen bonds are there? 3 of them. So 3 bond pairs and how many lone pair? 1 lone pair. Yes, you can understand this way also. Z is equal to bond pair plus lone pair. Okay. Z is equal to 4. How many bond pairs are there? 3 of them. So how many lone pairs are there? Lone pair is equal to 4 minus 3 is equal to 1. This way also you can do it, formula method, or you can understand this way. Out of 4 of 4 Z value, out of the Z value 4, 3 is bond pair and remaining is 1 that will be lone pair because there are only 3 bonds in 3 NH bonds. 3 NH bonds are there. 3 NH bonds are there, 3 of them, and rest 1 is the lone pair. Okay. Now the next one is water. Here oxygen is bonded to how many hydrogens? 2 of them. So how many bond pairs are there? 2 bond pairs. So remaining 2 of them will be lone pair. You can also do this way. 2 bonds. There are 2 bonds, right? This is 1 bond, this is 1 bond. So 2 bond pairs. So Z is equal to 4. Z is equal to bond pair plus lone pair. Z is equal to 4. How many bond pairs are there? 1, 2. Plus lone pair is, we need to find. So lone pair is equal to 4 minus 2, which is equal to 2. So 2 bond pair and 2 lone pair. Any way you can do, either way you can do. Now, here, just wanted you to understand that all of them, they are sp3 hybridized, right? Whether they have lone pair, whether they don't have lone pair, they are all sp3 hybridized because the Z value is 4. Okay. And also the Z value is 4. So the geometry is what? Geometry is tetrahedral for all of them. Okay. Here, Geometry is nothing but it is the arrangement of lone pair and bond pair. So that means geometry depends on both bond pair and lone pair. So what is geometry? It is the arrangement of lone pair and the bond pair. And geometry depends upon both bond pair and lone pair. Okay, so all the three of them have tetrahedral geometry. Okay, now here, carbon. I have here suppose I draw a methane molecule here, the tetrahedral structure of methane. Okay, and we just calculated over here that methane has 4 bond pairs. So methane, 4 bond pair, 0 lone pair. We calculated this just now. 4 bond pairs means 1, 2, 3, and 4. These are the 4 bond pairs. There's no lone pair, right? So, and we also calculated, we also saw in the last video that the bond angle is 109.5 degree, right? All the bond angle in methane is 109.5 degree, right? This is in case of methane, right? But in case of ammonia, ammonia has 3 bond pair, we just calculated now, and 1 lone pair. So these are the 3 bond NH bonds of ammonia with 1 lone pair of electron, lone pair, right? Now, this is ammonia. What is the geometry? Geometry is tetrahedral, just like methane, tetrahedral. And this is also sp3 hybridized. Now, if the geometry is tetrahedral, okay, the bond angle should have been 109 for ammonia also, but it is found to be 107 degree. That means it is less than 109.5. Okay, this is ammonia is also tetrahedral, methane is also tetrahedral. But why there's a difference in bond angle? Bond angle here is 109.5. Why in ammonia it is less? It is seen to be 107. Okay. Now, similarly, in case of water, oxygen, these are the 2 bond pairs of water. So it has 2 bond pairs and 2 lone pairs. Just now we calculated. So this is the 2 lone pair of water, and these are the 2 bond pairs. This is 1 bond pair, this is another bond pair. And here also it is sp3 hybridization, and the structure, it is geometry. The geometry is tetrahedral. The geometry is tetrahedral. Here also sp3 hybridization. So here also the bond angle should have been 109, but it is seen to be 105 degree. Okay, so the bond angle in case of ammonia and water should have been 109, but it is seen to be lesser. Yes, so that's what hybridization and valence bond theory said. But it is less than 109.5 degree. It is not like methane. It is less than methane. For ammonia, it is 107 degree, and for water, it is 105 degree. Okay, why this difference? Why this difference in why this difference in the bond angle. Why this difference? Why all of them have the same geometry, tetrahedral, but still they have different bond angle? Okay, now this is because of different kinds of electron pair. Okay, for example, so why this difference in bond angle in methane, ammonia, and water? Because of different kinds of electron pair. So we will be talking about this now. Okay, so coming to methane. This is the methane, tetrahedral geometry of methane. Now, this is one bond pair. This is another bond pair. This is another bond pair. This is another bond pair. All these four bond pairs, all these four electron pairs, or bond pairs means it's the electron pair only, right? One pair of electron is making this bond pair, right? So all these four, this is one electron pair, second one, third one, and fourth one. All these four electron pair are bond pairs. All the four bond pairs, all these four electron pairs are what kind of electrons? Bond pair electrons. So 1, 2, 3, 4. In all these four bonds, there are four pairs of electrons, right? All these four pairs of electrons are of the same type. What kind of electron pair it is? Bond pair electrons. Yes. But in case of, this is the first case. In case of ammonia, there's a lone pair of electron. And how many bond pairs are there? 1, 2, 3. 3 bond pairs are of same kind and one lone pair is of different kind. Similarly, in case of water, I have oxygen bonded to 2 hydrogen atom, 2 bond pairs plus 2 lone pair. So these two are different kinds of electron pair. So that means these different kinds of electron pairs. So the different electron pair decides the bond angle. So the bond angle is decided by whom? The electron pair, the presence of bond pair, the presence of lone pair, etc. Okay, so if there is a lone pair present, so if lone pair is present, then there can be difference in the bond angle. Okay, so students, here we just saw that methane, ammonia, and water, although they have the same geometry, that is tetrahedral geometry, they all seem to have different bond angles, as you can see. It is not similar. Ammonia and water bond angle is not same as that of methane. So we are checking on why is this difference. This difference is because of what? This difference is because of the different electron pairs. The electron pairs. That means bond pairs and lone pairs. If there are lone pair present, then the bond angles can be different. Okay, so we have to think beyond the hybridization. And what is this shape? And the presence of lone pairs can bring about changes in the bond angle. Okay. Now, coming to shape. What is this shape? Shape is nothing but the arrangement of atoms around the central atom. Shape is nothing but arrangement of atoms around the central atom. Okay, so geometry, we just saw. Geometry means what? Geometry is the arrangement of bond pair and lone pair. Shape is just the arrangement of atoms around the central atom. Okay, so in ammonia, now we are talking about the shape. There are 3 bond pairs, okay, and 1 lone pair. So we are ignoring the lone pair when we talk about the shape. Shape does not depend upon the lone pair. Okay, so we talk about the bond pair. So shape is the arrangement of lone pair around the central atom, and shape does not depend on lone pair. Okay, so I'll just write it as an important point. This is one important point. Shape does not depend upon what? Lone pair. Shape depends on only on the surrounding atom. If we talk about surrounding atom, that means it is what? It is bond pair. It is bond pair. This was about shape. Okay, so these are 2 key points about the shape. And what about geometry? Geometry depends upon both bond pair plus lone pair. It is how the bond pair and lone pair is arranged. So students, geometry depends upon both bond pair and lone pair, but shape depends upon only the surrounding atom, that is nothing but bond pair. It does not depend upon the lone pair. Okay, so talking about ammonia again. Okay, so these 2 about shape, and these 2 information about shape and geometry you must remember, because today's topic we will be talking about geometry and shape. How in shape we don't consider the lone pair, but in geometry we consider the lone pair. Okay, so in case of ammonia, we drew the ammonia molecule like this, right? And this is the lone pair, right? But the geometry is tetrahedral because it depends upon both bond pair and lone pair, right? But when we consider the shape, we ignore this lone pair. And now what is the shape? Is it looking like a pyramid? It has a pyramid shape because we ignore the lone pair. We consider only the bond pair, right? Again, I will write it down here so that I can talk about all 3 molecules. Yeah. So geometry is tetrahedral because it depends upon both bond pair and lone pair. And the shape depends upon only the bond pair. It is what? Pyramid shape. Right, pyramid shape. So I'm rubbing this. Now, water. Water is oxygen, hydrogen, hydrogen. It had two lone pair, right? What is the geometry? Geometry is tetrahedral because it is depending on both bond pair and lone pair. But in case of shape, what do we do? It depends upon only the bond pair. So we need to ignore the lone pair. Now, what shape is this one? This is nothing but we call the shape as bent shape or angular shape or V shape also. Okay. Now, the third one we discussed was methane. In methane, there are 4 bond pairs and 0 lone pair. Now, the geometry is the same, that is tetrahedral. Now, because geometry depends upon both lone pair and bond pair, right? Now the shape, what would be the shape? Because over here, the lone pair is 0. If the lone pair is 0, then students, the shape is same as geometry. In which case, when the lone pair is 0. Now in this case, the lone pair is 0. In methane, the lone pair is 0. The shape is same as geometry, which is tetrahedral. So this is one of the rules that you must remember. Okay, so geometry depends upon both bond pair and lone pair, but shape depends upon only the surrounding atom, which is bond pair. Okay, and if there is no lone pair, 0 lone pair, then the shape is same as geometry. Okay, now I hope it is clear till now. And when we talk about the shape, we just ignore the lone pair. We don't consider the lone pair when we talk about shape. Now, the next question is why there is change in angle. We saw that in methane, why there is change in angle. We saw that in methane, the bond angle was 109 degree. In methane, the bond angle was 109.5 degree. In ammonia, it should have been 109 degree, but it is 107 degree. In water, it should have been 109 degree, but it is seen to be 105 degree. Why this change? The answer to this question is given by VSEPR, valence share electron pair repulsion theory. This theory explains the difference in these bond angles. Okay. Now, according to this theory, the electron pair, whether it's the bond pair, whether it's the lone pair, all of them, they try to be away from each other. They try to be away from each other. Why they want to be away from each other? To avoid repulsion. To avoid repulsion. And become stable. Okay, so in ammonia, let me take the ammonia here. In ammonia, there is one lone pair of electron, right? Now, in ammonia, the bond angle is 107 degree. In ammonia, the geometry is tetrahedral, but the shape is not tetrahedral. Because these electron pairs, by electron pair, I mean it can be bond pair or lone pair, or both of them. These bond pairs and lone pairs are different, or they have different kinds of repulsion. Okay? So, talking about ammonia, this is the lone pair, hydrogen, hydrogen, hydrogen. Now, these bond pair and lone pair, these are the electron pairs, right? The type of repulsion is different. For example, the repulsion between lone pair and lone pair is more than, so the repulsion between, just understand this now, we will be doing with examples. So the repulsion between lone pair and lone pair is more than lone pair and bond pair, which is more than bond pair and bond pair. So bond pair repulsion is minimum. So this is one bond pair, this is one bond pair. So the repulsion between them is minimum. So this is bond pair repulsion. And the repulsion between, this is lone pair and this is bond pair. So this is lone pair, bond pair repulsion. So this is lone pair, bond pair. This is bond pair. Right? So this particular rule you have to keep in mind, that the repulsion between lone pair is the greatest. It is greater than lone pair and bond pair, which is greater than bond pair and bond pair. Okay, so for example, in water, how many lone pairs are there? 2 lone pairs are there. So this is lone pair, lone pair. This is lone pair and this is bond pair. This is also bond pair. So now check. I'll use another color. The repulsion between lone pair and lone pair is greater. They try to repel as far as possible. They tend to be away from each other as far as possible. Is greater than, I'll use green color, is greater than lone pair and bond pair. Is greater than lone pair and bond pair. Is greater than bond pair and bond pair. This is bond pair and bond pair. Valence shell electron VSEPR, valence shell electron pair repulsion theory, is all about these kinds of repulsion and how they tell about the shape of the molecule. Okay. So over here now we can explain over here, now we can explain the bond angle should have been 109 degree, but it is 105 degree because the repulsion between these two lone pair is too much. It's the greatest, and they try to reduce the bond angle. Okay, so they try to repel from each other, and in that process, what would they do? They would shrink this, or they will push this bond pair near to each other. So this lone pair will shift or push this bond pair, and this lone pair will push this bond pair, leading to reduced bond angle. Okay, I hope this is clear. Okay, similarly, in case of ammonia, this is the lone pair. There is repulsion between the lone pair and bond pair. Okay, so this repulsion will push the bonds near to each other. So the bond angle should have been 109 degree, but it is 107 degree. Because this repulsion between the lone pair and bond pair will push the bond pair near to each other, resulting in reduced bond angle. Okay? That is why the bond angle should have been 109, but it is 107. So it's just pushing it. Okay? So suppose if you see here, this is water. Okay? So I'm just showing the lone pair. This is the lone pair. Okay? And showing the bond pair. Bond pair in some books it is 105. In some books they show 104.5. And this is the electron geometry. That is, geometry is tetrahedral, you know that. Now, just now we discussed that the shape, they are referring to the shape. We just ignore the lone pair, it has the bent shape. Now, this is the bond angle, 104.5 or 105. Now, it should have been what? 109 degree, but it is not 109, it is 104. Because of what? Because of the lone pair, bond pair repulsion. Because of the lone pair, bond pair repulsion. Similarly, if I have what we saw was ammonia. Yes, ammonia, yes. Similarly, geometry is tetrahedral, you know, the shape is pyramidal. The lone pair is, there is a lone pair, one lone pair of electron, and the bond angle is 107. Now, it should have been what? 109 degree, but it is 107 degree. Because of what? Because of lone pair, bond pair repulsion. Okay. In case of water, there is repulsion between lone pair and also repulsion between lone pair and bond pair. Right? In case of methane, you can see all the bond angles are equal, and both geometry and shape is tetrahedral because there is no lone pair, absence of lone pair. Okay, so the adjustment is only between the bond pairs. Okay, I hope till here it is clear. Okay. I hope till here it is clear. Till here, you understood that there is repulsion between the lone pair and lone pair, and which will push the bond pair near to each other, and that is why the bond angle is lesser than the expected one. So this is the valence shell electron pair repulsion theory. Okay, now let's check out the VSEPR theory. Okay, so we already decided, or we already learned that the electron pair always remain away from each other. They try to be away from each other. So electron pair always repel each other. Whether it is the lone pair, or lone pair, or bond pair, bond pair. They repel each other and try to remain far away. Okay, and we also saw the order of repulsion. Lone pair repulsion is always greater than lone pair, which is greater than bond pair, So lone pair is the greatest repulsion, and bond pair is the least. So basically, this is the summarized VSEPR. Okay. Then we also learned when we discussed methane, if lone pair is equal to 0, okay, because shape does not depend upon the lone pair, then geometry is the same as, or the shape is same as geometry. The shape is same as geometry. For example, methane. But if lone pair is not 0, then shape is not same as geometry. We saw in case of ammonia and water. Okay, we also learned that geometry depends on both bond pair and lone pair. That is Z, which is equal to Z. Okay, and how to calculate Z? We revised it today and we did it in the previous video as well. And if Z value is 2, for different Z values, we have geometry. If Z value is 2, then I have linear geometry. If Z value is, this was done in the previous video, 3, trigonal planar. This is linear. This is trigonal planar. If Z value is 4, we have tetrahedral. Z value is 5, trigonal bipyramidal. 3 of them in the same plane, one above and one below. Also, if Z value is 6, I have octahedral, which is like this. Okay, so this was about Z and geometry, which we did in the previous video. Okay, now Z value is equal to lone pair plus bond pair. Okay, and geometry depends upon both lone pair and bond pair. But if the lone pair is there, then geometry is not equal to shape. Okay, then the shape changes, right? Because the shape depends on only bond pair. Okay, we just saw if lone pair is 0, shape is equal to geometry. If there is lone pair, shape is not equal to geometry. We discussed this just a while ago. And these are the postulates, or these are the main points of VSEPR. Okay, so in short, because of lone pair, the shape changes. Because of shape changes. Why? Because of repulsion between electron pair. Okay, and we know the order also. Lone pair repulsion is greater than lone pair bond pair. It is greater than bond pair bond pair. Okay, so this was about the VSEPR theory. Okay, I hope till here it is clear, and this is what you must know. This is very, very important. Okay. Okay, students, now let's check out some geometry and some shapes of some Z values. Okay, so I make a table here with Z value. Okay, bond pair, lone pair, geometry, then I have shape, and then hybridization. Okay. Now, in case I have Z is equal to 2, okay, and there will be 2 bond pairs. Okay, suppose the Z value is 2 and there are 2 bond pairs and 0 lone pair. Okay, that means both of them are used to form the bonds. There's no lone pair. Then we learned when Z value is 2, the geometry is what? It is linear. So suppose there's an atom A. This is linear. This is the geometry we learned in the previous video. Okay, and the hybridization is SP. Okay, and we learned that when lone pair is equal to 0, geometry is same as shape. So it is linear. It is linear because the presence of a lone pair makes the angle. Now this is the first one. Okay. Second one is when Z value is 2. Okay. Out of 2 Z value, one is a bond pair, one is a lone pair. Okay. So it's like this. So one is a bond pair and one is a lone pair, like this. Okay. So in that case, so I draw like this. This is the bond pair. So here it can be any other atom, B or hydrogen or anything. So I'm just drawing the central atom. I've just assumed to be A, and this is the lone pair. Okay, and maybe this is another atom B. I'm just drawing the central atom. Okay, now the shape I have to just I'm just ignoring the lone pair. So the hybridization is still sp because the Z value is what? 2. Okay. Now, suppose I have Z value is 3. If Z value is 3, you know the hybridization is sp2. Okay. Out of Z value 3, 3 bond pairs are there. There are no lone pairs, suppose. Okay. So in that case, geometry is what? A trigonal. This is what we learned last time. Trigonal planar. Okay. Bond angle is 120 degree. Bond angle is 120 degree. Bond angle is 120 degree. Okay. Now here you can see lone pair is 0. So the shape is same as geometry. So same geometry I can write here. Right. So this is for Z equal to 3. Right. Now I'll check for the next case. When Z is equal to 3, yes. When Z is equal to 3, the hybridization remains the same, sp2. But out of 3, Z value 3, I have suppose 2 bond pair and 1 lone pair. Okay, so I have a lone pair here and 2 bond pairs. Okay. The geometry is the same. Yes, the geometry that it is trigonal, trigonal planar. The angle here will not be 120 degree. Okay, so let me draw these bond angles, bond pairs correctly, properly. This angle will not be 120 degree like the previous one. Okay, here it was 120 degree, right? But this here, the bond angle will not be 120 because there is repulsion between lone pair, bond pair. This repulsion will push the angles. So, because of which, so there is lone pair, bond pair repulsion, because of which this angle will be less than 120. Yes, and this angle, because it is pushing, this lone pair is, this is lone pair and this is bond pair. It is pushing, lone pair is pushing the bond pair. This angle is greater than 120 degree. I hope till here it is clear. Okay, the geometry is the same, trigonal, planar. Now, what about the shape? When we talk about the shape, this is the lone pair. I told you when we talk about the shape, we don't consider the lone pair, we ignore it. Now, what is the shape? It is bent shape or angular or V-shaped. Why? Because we ignore the lone pair. Okay. Moving on. lines are not coming straight. Okay. Now, coming again, Z value is 3. So the hybridization is sp2. Okay. Now I have 1 bond pair and 2 lone pair. Okay. So I have something like this, 2 lone pair and 1 bond pair. Okay. Or I can draw it the other way around just to beautify it a bit. Okay. So I have the 2 lone pair. Anyway, you can draw it. This is the bond pair. Okay. The geometry is the same, trigonal, planar. Here again, this bond angle, this is the lone pair, this is the lone pair. This is the bond pair. We learned lone pair, repulsion is more than lone pair, bond pair. So this angle, they will push each other so much that it will be greater than 120 degree. And here, this lone pair will push this bond pair in such a way that this bond angle is less than 120 degree. This lone pair will push this bond pair. So this bond angle is less than 120 degree. Okay. Now, the shape, coming to the shape. So this is B. These are the 2 bond pairs. Sorry, these are the 2 lone pairs. So if I ignore the 2 lone pairs, I have, it's looking like a linear sort of thing, right? So the shape is linear because I just ignore the lone pair. Okay. Now, writing a question, find the number of lone pair, hybridization, geometry, shape for, so many things you have to find out. For first one is SO3. Okay. So coming to the central atom, that is sulfur, 286. Z value, let's find out. Half of valence electrons of central atom plus there are no positive or negative charge. Neither are there any monovalent atom. So 3. Z value is 3. So Z value is 3. That means sp2 hybridization. So Z value is a sum of lone pair plus bond pair. So Z value 3. Lone pair, I don't know how much it is, but sulfur is forming how many bonds? 3 bond pairs. So lone pair is equal to 0. Okay. And geometry for sp2 hybridization is trigonal, planar, which is same as shape because lone pair is equal to 0. I hope it is clear. So sulfur, 3 bond pairs, no lone pair, and the bond angle is 120 degree. All these bond angles are 1 because all of them, they are the same electron pair or the same bond pair. I hope it is clear. Right. Coming to the next one, nitric acid. It's an acid, so you must remember the oxygen, one of the oxygen will be bonded to hydrogen. Okay. So, coming to the Z value, half. Nitrogen is 2, 5. So 5 plus there's no positive or negative charge, but there's one monovalent atom. So 6 by 2 is equal to 3. So that is sp2 hybridization. So Z value is equal to lone pair plus bond pair, which is 3 is equal to lone pair. I don't know how much it is. Bond pair. So suppose nitrogen is connected to 3 oxygen atom and one of the oxygen is connected to hydrogen because it's an acid. So how many bond pairs? 1, 2, and 3. So there are 3 bond pairs. So lone pair is equal to 0. So here also geometry and shape are the same because lone pair is equal to 0. So trigonal planar. So nitrogen, oxygen, oxygen, oxygen. One of the oxygen is connected to hydrogen. The bond angle is 120 degree, 120 degree, 120 degree. All the bond angles are the same because there is no lone pair. Similarly, if I give a question like this, NO3 negative, Z value is equal to half of nitrogen is 2, 5. 5 plus, there is one positive charge that I have to add. There's no positive, there's one negative charge that I have to add. There's no positive charge, there's no monovalent atom. So 6 by 2, which is equal to 3. So sp2. Now, Z is equal to lone pair plus bond pair. 3 is equal to lone pair plus bond pair. Nitrogen is connected to 3 oxygen, so 3 bond pairs. So lone pair is equal to 0. So it's the same story as the previous one. Sorry. It's the same story as the previous one. Shape and geometry are the same, which is equal to trigonal planar. Why? Because lone pair is equal to 0. Okay, and 1, 2, 3, oxygen, oxygen, and oxygen. This is 120, 120, 120. Okay, so suppose if I have another question, D, sulfur dioxide. Sulfur is 286. So Z is equal to half of 6 plus. There's no positive or negative, neither there is any monovalent atom. So 6, 3. So Z is equal to 3. That means it's equal to bond pair plus lone pair. Sulfur is connected to 2 oxygens. So 3 is equal to 2 plus lone pair. So lone pair is equal to 1. So just trying to shift the board. Okay. Now, if it is Z is equal to 3, that means it is sp2 hybridization, right? And the geometry is trigonal planar, but the shape will not be the same as geometry because there is lone pair, right? So, sulfur, this is the lone pair, oxygen, oxygen, right? Now, this bond angle should have been 120, but it is not 120 because there is repulsion between lone pair and bond pair. Lone pair and bond pair. So this bond angle, so this will shift, this will push, the lone pair will push this bond pair such that this bond angle is less than 120. Okay. And what is the shape? The shape, if we ignore this lone pair, it is bent or angular. Okay. I hope till here it is clear. Okay. Now, coming to Z value equal to 4. Okay, coming to Z value equal to 4. So this is the Z value, this is the bond pair, this is the lone pair, this is the geometry, this is the shape, this is the hybridization. Okay. When Z value is 4 and there are 4 bond pairs, and when Z value is 4, the hybridization, you know, it is sp3, right? Suppose out of Z value 4, all are bond pairs, there are 0 lone pairs. The geometry is tetrahedral, right? So this is tetrahedral. So this 3, I need space here. So geometry, shape, hybridization. Tetrahedral. Okay. Now, if lone pair is equal to 0, geometry is same as shape. So same as geometry. And the hybridization is sp3. Now coming to Z value 4, yes. But there is maybe 3 bond pairs. 3 bonds are there and 1 lone pair. Okay. So maybe something like ammonia. Okay, 1 bond pair. So the hybridization is the same sp3. The geometry is the same, tetrahedral. But the shape. For the shape, what I would do is I have to ignore this bond pair. Sorry, I have to ignore the lone pair. When I ignore the lone pair, it is pyramidal. Okay, it's like a pyramid. Okay, so let me write neatly. Pyramidal. Okay. Another thing is that because of this lone pair, bond pair repulsion, the bond angle will be greater than, it should have been 109 degree, but it is greater than 109 degree because of repulsion between lone pair and bond pair. Okay. Similarly, this bond angle is also greater than 109 degree. And this bond angle, because of bond pair repulsion, and also because this lone pair is pushing this bond pair, this bond this bond angle is less than 109 degree because this lone pair is pushing this bond pair. Okay, so now coming to the next case where Z value is 4, there are two bond pair, there are two lone pair. Okay, similar to water. Okay, hybridization is the same. It is sp3 hybridization. Okay, now two lone pair, two bond pair. Okay, the geometry is the same, tetrahedral. This lone pair will push this bond pair so that this angle is less than 109 degree. This will push, this lone pair will push this bond pair. Okay, so this bond angle is less than 109 degree. Okay, what about the shape? For the shape, I need to ignore this lone pair so that we call this shape as a bent shape. Okay, so I hope it is clear. Now, let's do some question. Same question, you have to find the number of lone pair, bond pair, hybridization, geometry, shape. So, methane, Z value is half of, carbon is 2, 4. 4 plus, there are no positive or negative charge, but 4 monovalent atom. So 8 by 2, which is equal to 4. So Z is equal to lone pair plus bond pair. So 4 is equal to, I don't know how many lone pairs are there, but I know there are 4 bonds. So lone pair is equal to 0. So it is sp3 hybridization. Because lone pair is 0, the shape is the same as geometry, which is tetrahedral. Okay, and when you draw, the bond angle are all equal. All the bond angles are equal. Okay, similarly, second one, if I'm asking for ammonia, third one, I'm asking for water. Okay, Z, half of, for nitrogen, 2, 5. 5 plus, there are no positive charge, there's no negative charge, but there are 3 monovalent atoms. This is half of 8, which is equal to 4. So if it is 4, it is sp3 hybridization. Yes. Z value equal to lone pair plus bond pair. It is Z is 4. I don't know the lone pair, but nitrogen is connected to 3 hydrogens. So 3 bond pairs are there. So lone pair is 1. So geometry is tetrahedral. But the shape is not tetrahedral because there is lone pair. Right. So I have nitrogen. There is 1 bond lone pair. There are 3 bond pairs, hydrogen, hydrogen, hydrogen. This lone pair will push this bond pair. Okay. This lone pair will push this bond pair. Okay. So this particular bond angle will be greater than 109 degree because lone pair will push the bond pair. Okay. And this particular angle, because this lone pair is pushing this bond pair, this bond comes closer to each other, so it is less than 109 degree. Okay. Now, about the angle, this was the story about the angle. Now, if we talk about the shape, for the shape, we need to ignore this lone pair. When we ignore this lone pair, it is a pyramidal shape. Okay. Coming to water, finding out the Z value, half of oxygen, it is 2,6. Oxygen is a central atom, that because it's less in number. I have 6 plus, there is no positive or negative charge, but I have 2 monovalent atom, that is hydrogen, so which is 4. So Z is equal to 4 means it is sp3 hybridization, right? Now Z is equal to number of lone pairs plus bond pair. I don't know how many lone pairs are there, but I know that there are 2 bonds, oxygen-hydrogen bonds. There are 2 of them. So lone pair is equal to 2. Now for sp3 or for Z value 4, the hybridization is, the geometry is tetrahedral. Now, coming to the shape, which is not same as geometry because we have lone pair. I have oxygen, 2 lone pair, 2 bond pair. This is the lone pair, this is the bond pair. This is the lone pair, this is the bond pair. So, this lone pair will push them. So, this bond angle is greater than 109 degree. Okay, so let's consider as there is also an angle here. Let's take it as θ1. Let's consider this as θ2. Let's consider this angle as θ3. Okay, so just tell me which theta angle or which angle will be more. Lone pair repulsion is greater than, this is lone pair, is greater than lone pair bond pair repulsion is greater than bond pair repulsion. So θ1, lone pair repulsion is greater than lone pair bond pair, that is θ2, is greater than θ3. Okay, I hope it is clear. Similarly, if I take CH3 minus, Z value is half of, carbon is 2, 4. 4 plus, there's no positive charge, but there's one negative charge I have to add, plus 3 monovalent hydrogen, 8 by 2, which is 4. So Z is equal to 4, that means it is sp3 hybridization. Geometry is tetrahedral. Okay, Z is equal to lone pair plus bond pair. 4 is equal to, I don't know how many lone pairs are there, but I know that carbon is connected to 3 hydrogens, so 3 bond pairs. So lone pair is equal to 1. Okay, so shape is not same as geometry. So I have carbon, so it's like ammonia. 1 lone pair is there and 3 bond pairs are there. Okay, so in order to guess the shape, I have to ignore the lone pair. And what shape it has? It has a pyramidal shape. For any molecule having 3 bond pair and 1 lone pair. Okay, students. Now, when the Z value is 5, we have a lot of cases with Z value 5. Okay. And I have 5 bond pair and I have 0 lone pair. Okay. So in this case, the geometry is 3 bond pairs in the plane, 1 above and 1 below. Okay. And this is the shape is, or the structure, sorry, is trigonal. The geometry is trigonal bipyramidal. The geometry is trigonal bipyramidal. And you know the bonds that are in the same plane, the bond angle is 120 degree, and the ones that are above and below, it is 90 degree. Okay. Now, if there are no lone pair, you know that the shape is same as geometry. Right. And the hybridization, you know, it is sp3d. Okay. And another information that I want to give is, this is called as axial bond. I'll use another color. This is called as axial bond. And this, the one that is above and below, is called equatorial bonds. Okay. So that the ones that are in the same plane, those are called as axial bonds, and the one that is above and below is called as equatorial bonds. Now let's discuss the next case where I have 5 bond pairs and sorry, Z value is 5, 4 bond pairs and 1 lone pair. The geometry is the same, trigonal bipyramidal. And I place the lone pair. Suppose this is the central atom A, and I place the lone pair in the axial position. Okay, and these are the other two axial bonds, and this is the equatorial bonds. Okay, and always the lone pair is held by one nucleus, and the bond pairs are held by nucleus of 2 atoms. Okay, so the lone pair is placed in the axial position, and this is the trigonal bipyramidal. Okay, the geometry will be the same, and geometry depends upon both lone pair and bond pair, and the hybridization is sp3d. Okay. Moving on to the shape. Shape depends upon only the bond pairs. Okay. So here there are 4 bond pairs. So I'm drawing the 4 bond pairs. So this is the lone pair. I'll just draw now. Okay. So this is the geometry. So what I do is I rotate it and place it like this, the lone pair. And what do I get? Yes, this is what I get. And to determine the shape, I have to ignore the lone pair. So what is the shape that I'm getting? I'm getting a seesaw shape. Okay, this is for 4 bond pair and 1 lone pair. This is for, don't have enough space here. This is for 4 bond pair plus 1 lone pair. Although the lone pair we ignore while determining the shape. The geometry is same, which is called trigonal bipyramidal, okay, and the lone pairs are placed at the axial position, okay, and please remember that bond pairs, no, suppose this is the bond pair, right? So these are held by two nucleus. The lone pair is held by only one nucleus. Okay, so just an information. Now, the hybridization is sp3d. Okay, now coming to the shape. Now, the shape is, so there are 4 bond pair and 1 lone pair, right? So, the shape that I have drawn, okay, so suppose this is the shape. I rotate it and I rotate it, and suppose I'm drawing it like this. Suppose I rotate it and I draw it like this. Suppose I rotate it and the lone pair comes on top, and I rotate it and I'm getting like this A. Okay, so I'm just rotating it to this side so that the lone pair comes on top, okay, and the other bonds also change. Okay, so this like this. So I have not changed the position of anything. I just rotated the molecule. Okay, so you can see I will ignore the lone pair now. So is it looking like a seesaw? So it has a seesaw shape. Okay, this is the seesaw shape. Okay, I hope it is clear. Okay, now this is 4 bond pairs and 1 lone pair. Similarly, I have Z value is 5. And I have, out of 5, I have 3 bond pair. This is the bond pair. And suppose I have 2 lone pair. The geometry is the same. Trigonal, bipyramidal. The hybridization is the same, sp3d. Okay, now here there are 2 lone pairs. Okay, I place it along the axial bonds. And then these are the other bond pairs, 3 bond pairs, right? So the geometry is the same, trigonal, bipyramidal, right? Now, over here, for the shape, this is the geometry. For the shape, what I do is, this is the molecule, right? I rotate this molecule and I get something like this. I'm just rotating the molecule. Okay, and I get something like this and I ignore the lone pair. What shape do I get? Am I getting a T shape? Yes, T shape. All these shape you have to memorize it. This is just for understanding. Okay, so this is the T shape of the molecule because of the lone pair. How many lone pairs are there? 2 lone pair. Hybridization is the same. Now coming to the next one, 5 bond pair are there. Z value is 5. Bond pair is 2. Lone pair is 3. Okay. And in that case, I have 3 lone pair. I'm placing it along the axial bond. And the 2 bond pairs are the equatorial ones. Okay. And so these are the equatorial ones, right? Bond. So just that's what I showed over here. So equatorial ones are the ones that is above and below the plane. Axial ones are the ones that are in the same plane. Okay. So the geometry is the same, trigonal, bipyramidal. This is the geometry. Coming to shape and coming to hybridization. Hybridization will be what? sp3d, because the Z value is 5. Now coming to shape, if I hide the lone pair, so suppose this is the molecule. Suppose if I hide the lone pair, what kind of shape is it is giving? Linear. Okay, I hope it is clear. So this is basically, these are memorizing things that you have to do. Okay, so this is memorizing that you have to do. So this particular is T-shaped. So these things you have to memorize it just for understanding. You can understand and do. So if you can memorize it, that would be better. Okay. And also please remember, the geometry depends upon bond pair plus lone pair, but the shape depends upon only the bond pair. Okay. Now, moving on further, just a small information. Suppose, in case I have PCl5 and xenon oxyfluoride. Okay. Both of them, the central atom is surrounded by 5 atoms, right? But in the first case, PCl5, all are identical atoms, same atom. But in the second case, all are not identical atom. So how do you decide where to place the atoms? Like for example, xenon. Okay, the Z value is what? Half of valence electron is 8 plus, there is no positive or negative, but there are 2 monovalent atom. So this is 5. So Z is equal to 5. So it is trigonal, planar, one above and one below. Okay. So in this case, where will you place the oxygen and where will you place the fluorine atom? Okay. So there is a rule that more electronegative atoms occupy the equatorial position. Occupy equatorial position. Okay, so that means fluorine is more electronegative than oxygen. So the fluorine atom will occupy the 2 equatorial position. So this, I told you, it is the equatorial position. Oxygen will occupy the axial position. Okay. Similarly, if I have PF3Cl2. Okay, it also follows the same rule that more electronegative atom will occupy the equatorial position. This is the equatorial position. There is one more fluorine, so we can place it over here, okay? And the two chlorine, I can place it in this axial, okay? So irrespective of the number of atoms, okay, always the more electronegative atoms are placed in equatorial position. Okay, because there's one more. I don't have place in the equatorial, so I placed it in the axial. But after putting the more electronegative atom in the equatorial, there is one more fluorine left that I placed in the axial position. Okay, so always this is a rule, more electronegative in the equatorial position. I hope it is clear. Now let's do one question. So same, find the number of lone pair hybridization, shape, geometry, etc. for XeO3F2. Z is equal to half of how many valence electrons are there? 8 plus for the central atom. That is xenon is a noble gas that will have 8 electrons in the outermost shell. There is no positive or negative charge, but 2 monovalent fluorine atoms. So that is 5. So Z is equal to lone pair plus bond pair. I don't know about the lone pair, but I know there are 5 bonds present. So lone pair is equal to 0. And hybridization is sp3d. So the shape is trigonal bipyramidal. I'm placing all the atoms are not same type. So I'm placing more electronegative at the equatorial position and the oxygen in the axial position. Okay, and the shape is same as geometry because lone pair is equal to 0. Okay, I hope till now everything is clear. Now, second one is xenon fluoride. Z is equal to half of 8 electrons in the outermost shell. There are no positive or negative charge, but there are 2 monovalent fluorine atom. Z is equal to 5. Z is equal to lone pair plus bond pair. So 5 is equal to, I don't know the number of lone pair, but there are 2 bonds. So lone pair is equal to 3. So because the Z value is 5, it is sp3d, and geometry is what? Trigonal bipyramidal. Trigonal bipyramidal. And the shape, I'm placing there is only one type of atom present. So that is fluorine. I'm placing both of them in the equatorial position and the 3 lone pair in the axial position. Okay. Now for the shape, if I hide the lone pair, what is the shape I'm getting? I'm getting a linear shape. Okay, I hope it is clear till here. Right. Now, moving on further, we have one more question left for this. Suppose I have xenon oxyfluoride. So Z value is half of, xenon is noble gas, 8 electron in the outermost shell. There's no positive or negative, but 2 monovalent. So Z is equal to 5. So 5 is equal to number of lone pair plus bond pair. I don't know the lone pair number, but I know that there are 3 bond pairs present. So the number of lone pair is 2. Now, because the Z value is 5, it is sp3d. And the geometry, which depends upon both lone pair and bond pair, it is trigonal bipyramidal. Okay. And the shape is not same as geometry because there's lone pair. So what I would do is I will draw the geometry. There are two fluorine because more electronegative fluorine will be in the equatorial position. There are two lone pair. Okay. Oxygen. Okay. And if I ignore this lone pair, the shape is what? It is T-shaped. If you ignore the lone pair, what shape do you get? Do you get something like this? T. If you rotate it, you get T, right? So that is the T shape. Okay, I placed the fluorine in equatorial position because fluorine is more electronegative. Equatorial position. I hope it is clear. Okay, so while guessing the shape or while talking about the shape, we ignore the lone pair because shape depends upon only the bond pair. Now, two more type of Z values. Z value 6. Okay. Z value 6. We don't have a lot of cases for 6. Bond pair 6. Lone pair 0. Geometry, that is Z value. Z depending upon both lone pair and bond pair. It is octahedral. We have done this, okay, in the last video. When Z value is 6, it is octahedral. So it will be something like this. Yes, and shape will be same as geometry because there is no lone pair, same as geometry. And it is sp3d2, the hybridization. Okay. Moving on further, out of 6, if there are 5 bond pair and 1 lone pair. Okay. Now, because it is symmetrical, lone pair can be placed anywhere. So I'm just placing it here. Okay. The rest of the bonds I'm drawing. Okay. The geometry is the same, octahedral. And the hybridization is the same, sp3d2. But the shape changes because there is lone pair. One lone pair is there. Shape depends upon only the bond pair. Okay, so suppose how to guess the shape. Okay, here and here. Here there's a lone pair. So suppose instead of drawing the lone pair here, I told you it's symmetrical, so I can draw the lone pair anywhere. Suppose this is the, okay. Now, if you ignore the lone pair, okay, if you see, it is like a square and a pyramid, right? So the shape is square pyramid. Square pyramid. This is for 5 bond pair plus 1 lone pair. So see, the presence of lone pair is changing the shape of different molecules, right? The geometry remains the same for one particular type of Z value, but the shape changes because of the lone pair. Now, coming to Z value 6, there are 4 bond pair, there are 2 lone pair. So in that case, I have the 2 lone pair, I'm placing it on either side like this. Okay, you can place it anywhere because it's a symmetrical molecule. The geometry is octahedral. The hybridization is sp3d2. The geometry is not same as shape because the shape does not depend upon the lone pair. So I have These are the two lone pairs, but I will ignore the lone pair and I'll just check. So I'll just ignore the lone pair. And if I just check the shape, it is coming to be what? Square planar. Square planar. Okay, so we have one case with Z value 7, only one case, but before that we will do 2 or 3 questions. Okay, so I hope it is clear. Okay, from Z value 6, not much of the question is asked, but you must be prepared. Okay, I'm coming to a question saying finding the number of lone pair, bond pair, hybridization, etc. for SF6. So finding the Z value half of S is 286. So 6 plus, there is no positive or negative charge, but there is 6 monovalent fluorine atom. So this is 6. So Z value 6 means it is sp3d2, and the geometry is octahedral. Okay, now Z value is 6, which is equal to bond pair plus lone pair. I don't know the number of lone pair, but I know there are 6 bond pairs. So the lone pair is 0. So geometry and shape are same because the lone pair is 0. Coming to XEF4, Z value half of 8 electrons in the outermost shell, plus there is no positive or negative charge, but I have 4 monovalent atom, 12 by 2, which is equal to 6. So sp3d2, yes, and the geometry is octahedral geometry. Okay, now Z is equal to number of lone pair plus bond pair. 6 is equal to, I don't know the number of lone pair, but I know how many fluorine atoms are connected, 4. So 6 minus 4 is 2. Now, the shape. So I have xenon, 4 fluorine atoms are connected, 2 lone pairs. So for the shape, I have to ignore the lone pair. So what shape do I get? Square. Shape is square planar. Shape is what? Square planar. Okay, now I hope it is clear. One more last case of Z value 7, and bond pair is 7, lone pair is 0. The geometry is pentagonal bipyramidal. From Z value 7, not much is asked, but then we have to be prepared. So pentagon we will draw first. Pentagon, okay. So, and then bipyramidal means one is above the plane, one is below the plane. Okay. So, because there is no lone pair, shape is same as geometry. sp3d3 hybridization. Okay. And there are 5 bonds of 72 degree. Okay, all these are 72 degree. 5 bonds that are 72 degree, and the plane that is above and below, that is 90 degree. Okay, the above and below plane, that bipyramidal thing, that bonds that are above and below the plane, that is 90 degree. Okay, and 5 bonds are of 90 degree. Okay, so for Z value 7 only, you have to remember this. Okay, so I hope students, valence shell electron pair repulsion theory is clear to you. Because of the presence of lone pair, there is repulsion, and valence shell electron pair repulsion theory is all about repulsion between lone pair, lone pair, lone pair, bond pair, and bond pair, bond pair. And because of this, there are different shapes to the molecule. Okay, so students, I hope it is clear. That's all for today. Thank you. Have a great day.